everyone. Today I am going to discuss about the difference of approach of Lagrangian formulation and Newtonian formulation for a classical problem. Suppose I am considering a classical system. In that classical system, suppose there are four particles having mass m1, m2, m3 and m4. Now if we consider that here for this formulation I will apply, or I shall apply Newtonian formulation, then for individual particle I have to calculate those quantity. Suppose I want to calculate the angular momentum of the system. So for individual mass or individual particles I have to calculate the angular momentum, and as angular momentum is a vector quantity, so we have to do the vector addition. Or for any physical quantity that is a vector quantity, that I have to calculate by the similar way. But the main problem is that if the particle number is less, here the particle number is 4, that is fine. But if the particle number is more, that is huge number of, that is there is a huge number of particles, then that will be problematic. So in that case, what we will do, we will apply the Lagrangian approach for the formulation of the classical system. In the Lagrangian approach, basically what we do, we basically calculate the total kinetic energy capital T of the system, total potential energy capital V of the system, and we define the Lagrangian of the system as capital L equals to capital T minus capital V. Now I am giving one example of a simple system, that is the 1D harmonic oscillator system. 1D harmonic oscillator system. Let us consider 1D harmonic oscillator. Let m is the mass of the 1D harmonic oscillator. If x function of t is the instantaneous displacement of the 1D harmonic oscillator, then the instantaneous velocity of the 1D harmonic oscillator will be v equals to dx dt equals to x dot. So the instantaneous kinetic energy of the 1D harmonic oscillator will be capital T equals to half mv square. You all know that. It is half m within first bracket dx dt whole square equals to half m x dot square. So basically the kinetic energy of the 1D harmonic oscillator system is given by capital T equals to half m x dot square. Now I have to calculate the potential energy of the 1D harmonic oscillator system. We know if x is the instantaneous displacement of the 1D harmonic oscillator, then the restoring force acted on the 1D harmonic oscillator, that will be equals to F equals to minus kx. And here k is the restoring force constant, and the minus sign comes because the restoring force acts against the displacement. So for small displacement dx, the small amount of work done dw equals to f dx equals to kx dx. Here we are neglecting the minus sign. So for the total displacement 0 to x, total work done is given by w equals to integration 0 to x dw equals to integration 0 to x kx dx equals to k integration 0 to x x dx equals to k into x square by 2 at 0 to x. That is basically half kx square. So the potential energy of the 1D harmonic oscillator is given by capital V equals to half kx square. So the potential energy of the 1D harmonic oscillator system is given by capital V equals to half kx square. So now we have got the kinetic energy as well as the potential energy of this system, that is capital T equals to half m x dot square and capital V equals to half kx square. So basically the Lagrangian of that system is given by capital L equals to capital T minus capital V equals to half m x dot square minus half kx square. Here x is the only generalized coordinate, so we will get only one Lagrange's equation of motion of the system for the generalized coordinate x. Now the Lagrange's equation of motion of this 1D harmonic oscillator system for the generalized coordinate x is ddt of within first bracket del L del x dot minus del L del x is equals to 0. Now here del L del x dot, that is equals to half into m into 2x dot. Basically this is very easy formulation, and del L del x is equals to minus half k into 2x, that is equals to minus kx. So the Lagrange's equation of motion of the 1D harmonic oscillator system for the generalized coordinate x is ddt of del L del x dot means mx dot minus del L del x, that is minus of minus kx is equals to 0. So we get mx double dot plus kx is equals to 0, or x double dot plus k by mx is equals to 0, equation 1. If we compare this equation to x double dot plus omega squared x equals to 0, that is the equation of well-known SHM, then we can get omega equals to within root over a by n, angular frequency of oscillation. The time periods of oscillation equals to 2 pi by omega, equals to 2 pi root over n by n. So this is one of the example of that Lagrangian approach. This is very simple example. So in many cases, suppose when the earth moves around the sun, then in that case there plays the central force. So there also we can consider the system of having total kinetic energy, total potential energy, and also we can define the Lagrangian here, there also, and then we can similarly formulate the equation of motion of the system corresponding to the Lagrangian. So this is very easy approach compared to Newtonian approach, because only kinetic energy and only potential energy of the system is needed here. So I think all of you have understood this approach and why this Lagrangian approach is different and how it is different from the Newtonian approach for the formulation of classical problem. So I think all of you have understood this video, and if you like this video, please like and share it and subscribe my channel, and if you have any question, then ask in the comment section. Hope all of you are fine. Bye.